Hi, my name is Daniel Kocher from the University of Salzburg in Austria, and I'm going to present our work on density-based clustering for large collections of sets. This is collaborative work with the Munich-based company Celonis SE and was partially supported by the Austrian Science Fund. To start off, let me briefly introduce density-based clustering by example. We are given a set of data points and want to identify so-called clusters. A cluster is a dense region that is separated by a low-density region. In our example, there are three clusters, red, blue, and green. The remaining data points are considered noise. In our specific use case, each data point is a set, and on the right-hand side, you can see two example sets, R and S. To assess the similarity of two sets, we use the Hamming distance, which is the number of elements that appear in only one of the two sets. In our example, the Hamming distance is 3 since the two sets share 4 elements. Our goal is to partition a given collection of sets into clusters. One popular algorithm to find clusters based on the notion of density is the dB-scan algorithm. dB-scan takes two parameters as input. Epsilon is a threshold that defines the minimum similarity of two sets to be neighbors, and min points is a threshold that defines how many neighbors are required for a neighborhood to be dense. Consider the example on the left-hand side with min point 7. We use epsilon to find the neighbors of our query point R. Since R has 7 neighbors, it is a core point, that is, its neighborhood is dense. The dB-scan algorithm randomly picks a point and expands its neighbors recursively if it is a core point. A cluster is fully identified when all core points in a cluster have been expanded. We call this dB-scan or neighbor-by-neighbor order. Indexes are used to accelerate the neighborhood queries, and typically these indexes are symmetric. That is, they return all neighbors for a given query point. For sets, however, the most effective indexes are asymmetric. That is, they only return a specific part of the neighborhood with respect to a specific processing order. For a particular set R, we can split the neighborhood into processed and unprocessed sets. Asymmetric indexes only return the unprocessed neighbors for the current set R. We call this part the look-ahead neighbors of R. Our example shows the candidate regions for both index types and the look-ahead neighbors in contrast to all epsilon neighbors for a given set R. The indexes produce candidates that undergo verification to find the neighbors. For both candidates and neighbors, the asymmetric indexes only consider unprocessed sets and are therefore more effective. Unfortunately, asymmetric indexes are not compatible with dB-scan as the order is defined by the neighborhood expansions. One solution to leverage asymmetric indexes is to compute the neighbors with a set similarity join and execute dB-scan on top. However, this solution must materialize all neighborhoods, which requires quadratic space. Therefore, we propose an algorithm called spread. Spread uses asymmetric indexes to partition the given collection of sets into dB-scan clusters while requiring only linear space. We impose a processing order that is compatible with asymmetric indexes and use the look-ahead neighbors to retrieve each pair of neighbors once. Unfortunately, the look-ahead neighbors are not sufficient to deduce the clusters. We introduce the concept of backlinks to store enough information to deduce the clusters correctly. Finally, multiple subclusters may grow independently since we do not follow the neighbor-by-neighbor order. A spanning tree is used to merge these subclusters eventually. On the next 3 slides, we use a running example to describe 3 problems that must be solved and to show how spread addresses these problems by propagating information forward to unprocessed sets. Consider this example with 10 sets, a maximum Hamming distance of 3 and min points 4. We impose a length-based processing order, largest to smallest, that is, R1 is the largest set and is processed first. Core points are filled and all the points form a single cluster. The first problem is that we may miss points at the border of a cluster due to our processing order. For example, R1 is processed first and all other sets are unprocessed. R1 sees R3 as look-ahead neighbor, which is fine. When we move on, R3 will become a core point, but will not see R1 because R1 is already processed. Consequently, R1 would falsely remain noise. Therefore, we store a link from R3 to R1 when R1 is processed. In other words, R1 propagates the necessary information to its look-ahead neighbors. The backlink allows R3 to see and cluster R1, although it is not part of R3's look-ahead neighbors. We also found that storing at most min points backlinks per set is enough, therefore retaining linear space. Our second problem is the correct identification of core points. In our example, we move on to R5. Based on the look-ahead neighbors, R9 and R10, R5 cannot be classified as a core point because R5 sees only 2 out of 3 neighbors, and min points is 4. However, R2 is also a neighbor of R5. To address this issue, we maintain one counter per set that represents the density of its full neighborhood. When we process R2 and see R5 as look-ahead neighbor, we increment the counters of R2 and R5. This is possibly due to the symmetry of the distance function. Again, we propagate information from R2 to its look-ahead neighbors. After processing R5, the counter is 4, and we can classify R5 correctly as core point. Finally, we need to merge subclusters that grow independently but belong to the same dbScan cluster. We move on to R6 of our example. Before processing R6, there are 2 independent subclusters, C3 on the top and C5 on the bottom. We classify R6 as core point because it has 4 neighbors, and R6 already belongs to subcluster C3 on the top. As can be seen, R6 sees a neighbor of another subcluster that is R10. In the case that R10 becomes a core point, we must merge the 2 subclusters eventually. Therefore, we maintain a spanning tree of subclusters that must be merged and use a disjoint set data structure to retain linear space. This concludes the algorithmic part of spread, and we continue with some experimental results. In our experiments, we compared spread against 2 competitors. SimClust executes a traditional dbScan with symmetric index, and on the other hand, JoinClust uses the efficient asymmetric index in a set similarity self-join, materializes the neighborhoods, and executes dbScan on top. We executed our experiments on 13 different real-world datasets and multiple parameter configurations. In this talk, we show our results for varying values of epsilon over 3 datasets: BMS-POS, COSOVAC, and Celonis-1, which is a large dataset from the process mining domain. Min points is fixed to 16, and none of the solutions was sensitive to this parameter regarding runtime. The plots show the runtimes on the y-axis over the epsilon values on the x-axis. We observed that SimClust is clearly outperformed by JoinClust, which was to be expected due to the asymmetric index. Interestingly, spread is as fast as JoinClust in almost all instances, despite the overhead to deduce a correct clustering. Next, we show the memory consumption for the same configurations and datasets. The memory consumption is the heap peak of Linux mem usage and is shown on the y-axis. With respect to memory, JoinClust is clearly outperformed by both SimClust and spread. For higher values of epsilon, JoinClust consumes more memory and runs out of memory for the COSOVAC dataset, which is due to the materialization of the quadratic-sized neighborhoods. Instead, spread shows a memory footprint that is as low as the one from SimClust, and it does not increase with epsilon because only a single look-ahead neighborhood is materialized at a time, like in SimClust. Consequently, our experiment suggests that spread combines the best of the 2 worlds. It is as fast as JoinClust and as memory efficient as dbScan. Now let me conclude this talk. We discussed the problem of partitioning a collection of sets into dbScan clusters. For sets, the most effective indexes are asymmetric, but asymmetric indexes are not compatible with the neighbor-by-neighbor order of the dbScan algorithm. To leverage asymmetric indexes, a set similarity join must materialize the quadratic-sized neighborhoods and execute dbScan on top. We proposed Spread, a DB-scan compliant clustering algorithm that combines the best of the two worlds. Spread imposes a specific processing order, and hence Spread is able to use asymmetric indexes. In our experiments, Spread is as fast as the join-based solution while retaining the memory efficiency of the DB-scan algorithm. This concludes my talk, and now I'm happy to answer any questions.